something on this side?
No, no, there is a video here. No, it's good.
Go ahead. This one. So you can change side with this thing. Okay, but it works though, so you can have just one here or
Okay. Good afternoon. I'm Davide De Marchi from the European Commission, and I will give a talk on Voila meta dashboards for streamlined geospatial data visualization. I work for the European Commission at the Joint Research Center, which is located in northern Italy. It's abbreviated as JRC, and it's the Commission Directorate that provides independent scientific support to the EU policies. We are around 3,000 employees with a high percentage of researchers, and we are located in 5 different member states: Italy, Germany, Belgium, Spain, and the Netherlands. JRC focuses on a wide range of research topics surrounding the various EU policy goals. This includes areas like climate change, energy, digital transformation, health security, with in general a strong emphasis on sustainable development and innovation. We have, since I see here many young people and we are in a university, we recruit a lot new forces. So I invite you to see the opening of posting in the Commission, because it's a wonderful place to stay, and in particular the Joint Research Center, which is the research focus of the Commission. In recent years, the JRC, I'm sorry, it's not my PC, so okay. In recent years, the JRC has created an internal cloud platform that serves the need for storage, processing, and data analytics activities of the different research groups. It's called BDAP, a Big Data Analytic Platform, and one of the services of the BDAP platform, one of the services of the BDAP platform is the Jupyter Lab service, which enables researchers to perform interactive data analysis, mainly in Python, but not only in Python. And on top of the Jupyter Lab, we selected Voila as the preferred tool for scientific dissemination and communication of scientific results, because we think it allows for the easy creation of interactive applications to visualize complex data sets that are produced by our colleagues. And for those who do not know, Voila is an extension of Jupyter that converts a notebook into a web application, a standalone application. It does this basically rendering the notebooks without showing the cell codes, the codes inside the cell. Only the output of the cell is displayed. We love it a lot because it allows to have a single environment where you can do full data analytics workflows, but also communicate your results. So it's a very common way to pass from experimenting to communicating your results. Widgets are the building block that enable to create interactive application and to capture the user input. Jupyter standard widgets are the EuroSciPy widgets library, which are perfectly fine for creating exploration dashboards. But in order to provide a better user experience, modern libraries can be used, more modern libraries can be used. Like, for instance, the EuroSciPy Utify, which you see here a screenshot. The EuroSciPy Utify is a porting of the Utify.js JavaScript framework into the Jupyter Python environment. These widgets are highly customizable in size, color, variants, themes, etc., and can be aggregated in more complex structure. For instance, you can build a list that contains buttons, and each button can contain an icon, etc., at any level of inclusion. EuroSciPy Utify is extremely powerful, but not so simple to use, and the documentation requires the user to always jump from JavaScript to Python, so the usage is not so easy. For this reason, we have created the library, the visualization library, which is called Voice Library, and we have released it as open source in the code.europa.eu, which is the platform for the open source code of the Commission. Here you can find the link to the code and to the documentation, and of course you can install the library by pip install voice or conda forge install voice. So it's present both on pip and in conda forge. Which are the components of this library? As I said, the EuroSciPy Utify widgets are used to create the interface element, so the upper part of the slide. But since many of the apps that we create have geospatial component, we need an interactive map to display raster and vector data, and we selected EuroSciPy Leaflet, which is a port of the famous Leaflet.js JavaScript library into the Jupyter environment. Of course, talking about visualization and dashboard, you very often need to show charts, and for this we use a lot Plotly. But in cases where Plotly, we love Plotly, it contains a gallery with hundreds and thousands of examples covering many needs. But in case what Plotly does is not sufficient, we create charts by using SVG and CSS3. And we use a small library that is called EuroSciPy Events, which enable to create interactive charts using SVG. So you can manage to capture click and mouse move events, or all mouse events, at Python level using this EuroSciPy Events library. Why we use SVG? Mainly because sometimes we need to have responsive charts. So charts that adapt their dimension according to the dimension of the screen, which is quite difficult to do with Plotly and with many other charting libraries. But with SVG, it's born exactly for this, so for being responsive. So the objectives of the voice library, here there is a list. I will not go in full detail, but the good thing about voice is that it allows you to create full screen pages, so pages that occupy the full screen. It supports responsiveness, so it enables you to create a dashboard that behave well in phones, small screen, big screen, etc. It has a lot of, it helps you in creating layered components, what I mean, dialog boxes. So you can have a dashboard where you don't need to alternate pages, but you can keep the main pages on the back and have dialog boxes that pop up on the screen. So they give to you an experience which is very similar to the experience of the desktop application. Last point, it enables you to create multi-page application, which is the focus of this talk. This is I hope it will start. Okay, this is a video. This is an example of the type of application that you can create with the voice library. This is a dashboard for the visualization and validation of an important agricultural data set, which is called Lucas, which is set up by EuroStat. Lucas means Land Use, Land Cover Statistical Survey. And the aim of this project is to collect harmonized data on land cover and other environmental parameters across the European Union. And this data is crucial for doing policy decision related to agriculture, environment, and sustainable development. These data of Lucas are acquired in through extensive field visits on around 100,000 points in all European countries, and the agronomists visit the points and for each of them collect what is present in a grid of 41 points around the main point, 41 locations around the visited points. As probably, okay, I will. It's better if I start. I can start the video. This is the main page of the application, and there are three main sub-pages. So, this is an example of a multi-page application. And in this first page, you can see two geographical viewers that work in accordance. In one, you have an overview, and the other, you have the specific point that is selected with its 41 points around it. You have in this part of the screen an SVG chart where you see the landscape features, so the elements of the landscape that are not agriculture, that is the topic of this dashboard. In this case, you have 5 points that are green, that are trees, and 4 points that are grass, yellow, okay? So this is an example just to give you an idea, because this is a visualization of a data set that is quite complex. It's a multimedia data set. We have pictures taken on the ground. We have a PDF that is associated to each one of these 100,000 points. So these are examples of dialog boxes that pop up from the screen. So this type of application, which seems like applications that are desktop application or web application developed with a lot of JavaScript code, in reality are in reality, this is a Jupyter notebook, even if you don't see it. This is the structure, the structure of this dashboard, where you have the Jupyter notebook and some additional Python classes that manage the viewer, the editor. There is another function that enables users to validate the interpretation that was given on the field, etc. The connection to the DB, specific widgets that are created precisely for this application. So inside the BDAP, this big data analytic platform, we have set up what we call VAS, Voila as a Service. So we have set up an automated pipeline for autonomous deploy of dashboard in production directly from the BDAP GitLab platform. So the user develops its dashboard, its Jupyter notebook with the accompanying Python code, configuration file, etc. And by simply pushing on the repository, an automatic procedure puts the dashboard in production. So this enables us to create a community of dashboard developers that spawn different fields like AI, agriculture, equality, disaster management, etc., transport, etc. All of these share the importance of geospatial data visualization. But since Voila is not a point-and-click dashboarding tool, so it's not something like the tools that create dashboard without programming, there is a steep learning curve. So in order to help our users that are not professional programmers, they can be just I don't know, geologists or agronomists that do part-time programming. So we tried which is the core of my presentation, we tried to set up this concept of meta dashboards. What are these meta dashboards? Are web applications developed using Voila itself, so they are still dashboards, that automate the creation of dashboards. or at least help in the creation of dashboard. So they provide a what you see is what you get tool to create the front page of your application, the specific geographic page that will be open from the front page, and so on. So you work in a dashboard visually, you configure your application, then you save your .py, .ipynb, and .json file from the selection that you have done, and that's it. Then these elements constitute the initial framework of your application. Let's see how it works. This is the main helper, so this is a video. It's a dashboard, as you can see. Maybe it's not so clear, but there are two buttons. The first button opens the configuration of the front page, the main page of the application. Here you can select, for instance, I don't know, the name of the application, the title, the subtitle, the dimension of this part of the title window, the opacity, etc. So in a visual way, you select how your front page will appear. Then you go to the background tab. You have the selection of around 100 possible background images, but you can also import an image that you want. So it's what you see is what you get editor of your front page. Then you can go in the buttons tab and you can create buttons. In this example, we create a button called function 1. So having the title function 1, the subtitle 1, and then you put the name of the Python function that this button should call. So let's call F1. So the button appears on the page. You can create a second one with in the same way. Let's let the video go on. So function 2, subtitle 2, and the function to be called will be F2. Okay? You can also add an image to each button. Then you can edit the dimension of the button, the opacity, the width of each button. So they are automatically positioned if they are bigger than the row, etc. When you are then, okay, you can work on the credits, so you can change the message credit that appears here, etc. When you decide to save, you save locally, so you basically download, because this is a cloud system. You download two files. Okay, you download two files. One is the ipynb, and one is the .json. The .json contains all the selections that you have done, and the ipynb contains few snippets of code. In this case, where you have the two functions, F1 and F2, that open simply a message, but they are placeholder for the code that you have to insert. When I don't know if the video is still going. Okay. If you execute in Jupyter Lab this snippet of code, here is highlighting the fact that the JSON file is open. And the JSON contains all the information that we have inserted, for instance, the two buttons, the button 0 and the button 1 with the title, subtitle, and the name on click, the name of the function. When we execute this cell, our front page appears. So it's a very simplified way to create a front page, which is, like, I don't know if it is attractive or not. So but it has some visual appearance. You can have your logo, etc. The second helper is the second button in this application, which is called Page Configurator. It's a little bit more complex because it enables you to. It's focused on creating a geospatial page, so a page where you display some geospatial data. And on the left, you can select the title of the application, the subtitle, You can select the primary color and the secondary color, or you can let the application to select automatically the secondary color. And then you can have 1, 2, or 3 panels for positioning your windows. In this case, if you select 3, you have 3 foldable panels where you can put your windows. Okay, you can also work on the content on the main page, so you can have 1 element, 2 elements, 3 elements, positioned in horizontal, vertical, etc. So in this example video, you can have, for instance, you can create 2 maps that work together, so that are coordinated in. So when you move in one map, the other one moves at the same time. Okay. And you can add the node SVG drawing, plotly charts, etc. in other part of the window. Okay. And that's it. We can skip. We go to the now. Okay. When we go here and we do the download, we have this time 3 files. We have a JSON, a .py, and a .pymb, and the way it works is the same. You import it in Jupyter Lab. You can examine the JSON with all the selection that you have done, and you can execute the IPyMB, and you will have exactly the same. So in this case, it creates a class where there are placeholders for you to insert your code. Since time is flying, I prepared 2 or 3 examples of real dashboard creating this way. I will show just one. I skip some of them. Just show this one, which is a dashboard created using these tools for the Fair Mode project. The Fair Mode is a European forum on air quality modeling. So it puts together all the experts on monitoring of air quality in Europe. Air quality in Europe is a big problem. There are a lot of deaths, a lot of people that suffer from bad quality of the air, especially in the northern part of Italy, in Belgium. There are a lot of areas that are industrial, etc. This Fair Mode has the scope to analyze if the models created by different research centers in all Europe are fit for purpose. So if they cover well the observed values in air quality stations. So here you can see on the left the list of models for a particular pollutant like NO2, ozone, or PM 2.5, PM 10. You see all the list of models created by different research institutes. Then when you click on one, in this case one covering the Pianura Padana, the northern part of Italy, you can see the raster, which is the model, and the points that are the stations, the observer station. Here it is interesting because there is a custom chart created in SVG, so responsive, etc., where the click and the move of the mouse is captured through this IPy events library, and the map and the chart work in agreement. And let you examine the synthetic value of this NQI, which is a value of fitness of the how well the model fits the observed value in the stations. So last slide. Okay, I have other 2 examples, but I've skipped it, so I think I'm on time. What are the takeaways of this presentation? Voila. I think that Voila demonstrates that its ability to create real-world web applications, so applications where you have to do with complex data sets, multimedia data sets, images, geospatial data, tabular data, etc. The voice library, which is quite used inside the Commission and the GRC to communicate scientific results to the hierarchy or to the public. We think it's a good tool for extending the capability of Voila and simplifying the creation of Voila dashboards. The meta dashboard that I have presented are tools that can help non-professional programmers to start this path of developing complex applications using 100% Python. I think I'm on time.
Yes.
So thank you, and if you have some questions, I'm here.
Thank you so much, Davide. That is very nice talk. Do we have any questions from the room? Okay, then I have one because I'm actually curious about this other projects that you didn't have time to show during your presentation. Because I showed there was one about something about mountains, right? There was one for, like I showed like the word shirts, right? The one that was a project before the
one is called Sherpa.
Mm-hmm.
It's still another project for air quality monitoring, but in this case it is a project where the user of the dashboard can simulate the reduction of pollution in specific areas of Europe. So they select a target pollutant like PM 2.5. They select an area and they say they set what is the reduction in pollution that they want. Pollution coming from different sectors, residential, industrial, transport, etc. And the software has a Python model that calculates the target, the delta in concentrations in the different areas, in a raster, in a grid, let's say. And then it's very interesting because it enables you to see the cost that this reduction, the money that you have to spend to obtain this reduction, and the benefit that you gain in terms of less deaths, more healthy people, etc. So it's a cost-benefit analysis done in a dashboard, and it's used a lot in this community that has more than 600 participants. So it's a real application. So it's not a demo.
Yes, very nice to hear that the project that you created is like very widely used by the scientific community. Do you have any more questions? Yeah.
So I wanted to ask about the GRC. I noticed that there are a lot of publications by the center. So what kind of publications mostly are those? Is it based on this programming, or is it everything starting from geo data to like observations? Like, could you describe shortly?
Yeah, it is a research center where there are different groups. There are groups that work in biology, in chemistry, in monitoring of emission of cars, studying of the performance of electrical cars. So there is everything. It's a campus similar to this with many buildings, and we are just in Italy. We are 2,400 people working there, so it's quite big. Then there are other 5 location in Europe, but they are smaller, much smaller, 200, 300, 400 people each. So the production is quite wide. For instance, where I work on the first floor, there is the research laboratory for food contact materials. So materials that can come in contact with food. So plastics that are safe or not for children. So there are laboratories, there are a lot of things. But in general, it's the research institute that helps the politician in Brussels to put numbers inside laws. So every law that they set up, when there is a number, it comes from a research done in the JRC. So the emission of the cars next year should be less than this grams per kilometer. This number comes from research done in JRC.
So it's safety and regulations basically.
Yeah. Thank you. Thanks.
Let's thank Davide again.
Thanks.
Now the next speaker is Daniel.
I can use my just for some reason it didn't work on his laptop, so we switched to this one. Here, I have my. Oh, okay. So no. If you want, you can try with this. Okay. Doesn't matter which. It's usually C. Okay. Perfect. Okay. And after, I will show a little demo.
Yeah, sure.
I will duplicate the screen.
So please welcome our next speaker, Daniel, who's going to tell us about processing cloud-optimized and unstructured data in Python.
Okay, thank you. Hello everyone, and thank you for coming. I am Daniel Alejandro, and today I'm going to talk about a problem that many of us in the scientific Python community face, that is how to handle massive complex datasets without becoming a full-time cloud engineer. So we are going to explore who can process both cloud optimized and traditional structured data more efficiently. So the core idea is to turn the complexity of the cloud into something simple, powerful, and Pythonic. We will be looking at two key tools that we made, DataPlug and Fiber. But first, let me briefly introduce who we are and where this work comes from. This work comes out of Cloud and Distributed System Lab at Universitat Rovira i Virgili in Catalonia. We are a research group with over a decade of experience in this space, so we are not just an academic group. We are deeply involved in building real-world solutions. We did several large-scale European research projects. We collaborated with IBM or Dell. And we have a track record of publishing at top-tier conferences. But the most importantly is our goal is not just research for its own sake. We focus on building production-grade open source solutions. Some of you might be familiar with LitOps or serverless computing framework. So today we will focus on its sibling projects, DataPlug for data and Byron for workflows. And all of this is motivated by a single massive problem. And we call this problem the cloud complexity task. This is an invisible cost that we all pay with time, frustration, and money when we try to move our scientific workflows to the cloud. Think about the last time that you wanted to run your analysis on the cloud. How much of your time was spent writing Python, and how much was spent just fighting with permissions, networking, Docker files, among others. So this task shows up in several ways when we dealing with the tsunami of data that we face today. The problem starts with the data itself. We are living in an area of data tsunamis. Here, this screenshot shows the GDC portal with almost 9 petabytes of data. This is far beyond what a single machine can handle. And these datasets uses complex formats like FASTQ for genomics or LiDAR for geospatial. So these formats are highly specialized and crucially were not designed for the cloud. So the cloud promise is incredible. It promises on infinite on-demand computing and storage. So it's the perfect solution for this problem. But the reality is that bridging the gap between our complex data and the cloud power is notoriously difficult. So we are left with this equation. The cloud power is great, but cloud complexity is a huge budget. Study shows that developers and researchers often spend 40 to 60% of their time just fighting with the infrastructure instead of doing science. So this is the complexity tax, and it comes in three main forms. The first one is the complex cloud provisioning, simply setting up the necessary security roles, Docker containers, Kubernetes clusters, it's a full-time job itself. The second one is the complicated data access. This is a pain point. How do we efficiently feed these massive unstructured files into parallel frameworks? And finally, the dependencies here. We all been there, managing consistent Python environments with hundreds of workers, and an environment that works today could fail tomorrow. So this is a very big problem. For non-cloud native files, this complexity forces us to a very common but very inefficient workflow. And this workflow is the standard approach that is something called static partitioning. The workflow is painful because the first step is download the entire multi-gigabyte or terabyte file into your local machine. Then you run a script to split it into 1,000 smaller and manageable chunks, and then you upload all those small files back to the cloud. So as you can imagine, this is not optimal because you have a massive and expensive data movement. You are paying for network arrest and ingress. You are paying for duplicating the storage, and above all, and this is a key point, this method is crucially rigid. What happens if you choose the wrong chunk size? You have to do it all over again. So the key question is, what if we could create these data partitions without rewriting the data at all? And this is where our solutions comes in. We can achieve on-the-fly partitioning by combining two tools, DataPlug, which handles the data, and Pyron, which handles the workflow. But first, let's look at how DataPlug solves this. The core idea behind DataPlug is simple but powerful. What if we could create virtual partitions, virtual data partitions without ever rewriting the original data? To do this, first, DataPlug uses an extensive plugin system. This means that DataPlug understands the format-specific structure of each file, like FASTQ or LiDAR or another format. Second, it performs a dynamic partitioning. When you call the partition method, DataPlug doesn't move any data. It performs a fast metadata-only operation on an index file that it creates. So this means creating thousands of partitions is super fast, and importantly, zero cost to repartition with a different strategy or chunk size. And finally, it enables on-the-fly data fetching. This means that your parallel workers use this lightweight metadata, we call it data slice, and to make a parallel byte range HTTP request to get only the data that they need and don't read the entire file each worker. So this completely eliminates the massive data movement of static partitioning. And the best part is that all of this is completely hidden behind a clean Pythonic API. The first step is simple. Simply write the address of your S3 data to DataPlug and specify the decided format. In this case, we are pointing to a large compressed FASTQ file. The second step is to run this fast one-time preprocessing job. This is the step that reads the file once and then creates that standard smart and reusable indexes. And then here is the magic. To do this, you call the partition method. In this case, we will create 1,000 virtual partitions at runtime. Since this is only a metadata operation, it's incredibly fast. And the best of all is that you can experiment with different batch sizes at no cost. This is so important. And finally, inside your parallel function, the code that runs on each worker, you call the data slice point get, and this is the exact moment that the data is received listly from S3, and the workers only get the bytes that it needs, nothing more. And this simple and elegant API abstracts away all the complexities of parallel managing of non-cloud optimized formats that we have been discussing. But even with data plug, we still need to solve the workflow problem. We need to set up a parallel framework like DAS or lithops. We need to build a custom runtime with our libraries, pandas, numpy, and of course data plug. And then we need to deploy that runtime to hundreds of workers. So this is so complicated and bring us to this painful, the manual workflows that can take days or weeks. So this is why we built Pyron. Pyron is an iterated platform that solves this workflow problem. Think of it as an operating system for your scientific computing jobs. It provides some features. The first one is a unified environment, a complete VS Code interface in your browser. You don't need to set up anything in your local machine. Second, it has an automated runtime. You just define your dependencies in an environment.yaml file or requirements.txt, and then Pyron will build, version, and deploy that runtime environment for you. And the third one is it offers one-click execution. This means that the run button abstracts the entire cloud's lifecycle. It handles providing resources on your Amazon account or IBM account, running the code, monitoring, and cleaning up afterward. So you just focus on your code, and this is the objective of Pyron. But let me show you what this look like in practice with a quick demo. 1 second. Okay, this is Pyron. When you sign up into Pyron, you will need to link your Amazon account to Pyron. And then here we have some sections. This section is the pipeline section. Here you have some real-world examples like metadata, metabolomics annotation, geospatial analysis. Also, we have LLM execution with Olama. And the idea is simplicity, because you have all of these examples, and you can run it with just one click. You click on the run button, and then you can start working with this pipeline. But the most important part is the workspaces. The workspaces is the space where you have your projects, and this is working in your own Amazon account. We don't have anything on our platform. And here, for example, we have a data plug workspace. We open this VS Code interface. As you can see, this is a web interface. You don't have anything in your machine. And here we have a super simple data plug code. We have some steps. The first one is to point our FASTA file into S3. The second one is to make this one-time fast preprocessing job that creates the index file to have these reusable indexes. And then here we create 8 virtual partitions at runtime. It means 0 cost. We have a chunk size of 8, but we can change it to, you look it right? I think yes. We have a chunk size of 8, but you can change it to 12 or 18 or what do you want without 0 cost. And then we have here lithops using to deploy that function, the process data function with the data license that we process into a distributed system. Here, on the function that we will run on each worker, we only get the data slice and return it, so it's super simple. And another again, simplicity, the idea behind Pyron. You just click on the run button, and then it starts running on Amazon Lambda. Here you can see it's running on Amazon Lambda, and after a few seconds you will see the results of your data, your analysis here. And if we want to change the number of chunks, just click on the run button, and another game will be running with 18 number of chunks, super simple, super easy to use. And this is the part of the code, but 1 second. But it's super simple, the workflow of Python and DataBlack, but it is actually performant and cost efficient. So let's look at the benchmarks. The first one is to look at serverless or fast workload load. In this case, we compared Python against a leading competitor, in this case, Coiled. And the task was generating a chunk references for GOES satellite data, a common task in geospatial community. And the results are tricky. For this type of vastly parallel workloads, our approach is up to 5.4 times faster and incredible 50 times cheaper than Coiled. So this is because serverless is perfect suited for this, and Python make it seamless to use. But what about more traditional clusters with tasks? The story is similar because here we benchmark generating IPCC climate plots. We compare Python against Coiled, and we were 1.6 times faster in total time to results. And the key reason is for this is that Python cluster creation is 2.5 times faster. This is a huge productivity boost. It means you spend less time waiting and more time iterating on your science. And talking about DataBlack, comparing the core preprocessing step that DataBlack introduces and the traditional methods, the static partitioning that we mentioned before. On the left, we have the genomics data. Python on the file preprocessing is about 65% faster than the old static partitioning workflow. And on the right, with geospatial LiDAR data, the improvement is even more significant compared to common practice of first converting the LiDAR to cloud optimized formats like CopyC or something like that. DataBlack directly process it is 71% faster, and the metadata is is 99.8% smaller. Hello? Okay, perfect. So, to sum up, we have seen the challenge of the cloud complexity task and who on-the-fly partitioning with DataBlack and integrated execution with Python can solve them. So, what is the final message of my presentation? We have seen 3 key ideas. The first one is DataBlack solves the scientific data access problem with efficient on-the-fly partitioning. Second, Python solves the workflow problem, providing an integrated operating system for tools like DataBlack, Lithos, Task. And finally, the result is a workflow that is demonstrably faster, cheaper, and simpler for scientific cloud engineers. So we invite you all to try this out today. Please feel free to scan the QR codes. The first one will take you to the DataBlack GitHub repository. It's a fully open source solution. We welcome any contribution. The second one is the QR code that will take you to Python.cloud, where you can sign up for a free account and be running your code in less than 50 minutes, really, 50 minutes. And we believe that this combination of tools can fundamentally change who approach large-scale scientific analysis in Python. So this is all. Thank you for your time. If you have any question, I will be happy to answer it.
Thank you so much, Daniel. Do we have questions from the room?
Thank you very much for the talk. I was very interested in the use case for genomics. You mentioned FastQ files and so on.
Mm-hmm.
So some of the things I do with bulk RNA sequence processing. Yes, it's massively slowed down despite the innovations in the file format itself over the years. It's usually quite slowed down. It could be faster, ideally. The use case that I've got at the moment is where the data is stored on cluster storage on a high-performance cluster. Does that count as a cloud service in principle?
Can you repeat, please?
Okay, so we're talking about Amazon Cloud Services and so on, Google Cloud Services as the cloud. What about another remote service, such as a high-performance cluster, been locked in remote?
For your local storage, for example.
Well, utilizing data cloud to have to process in parallel large data streams.
Yeah.
So treating the HPC storage as a cloud storage.
You can add another extension to data plug to use this new storage. It's simple to add it.
Okay, fantastic.
So you don't need Amazon or IBM or Google Cloud. You can have your file in your local storage and then process it with data plug.
Okay, that's great. Thank you.
Thank you.
Any more questions? If not, let's thank Daniel again.
Thank you.
We still have a little bit of time, but our next speaker, Agnieszka, can slowly start to fight with technical difficulties. Hopefully everything will go smoothly and we'll start on time in a few minutes.
He linked back at some point. There's anybody who recognizes this. Yeah, basically, the minute of to me and not. And there was like one question that broke down. Then I'm sure oh, but I knew because there was even a complaint that said
Działa, a możesz też...
Się zastanawiam się,
Jeśli
ale
chcesz...
chyba...
A nie, skupiłem się do tego. Działa, możesz to zrobić. Jak się nazywa? Tak, jest pointer, a tamten...
Nie wiem, czy będę potrzebować, bo i tak muszę tutaj to zobaczyć to. Może trzeba... To nie wiem, czy zaczynać, czy...
Myślę, ja bym poczekał, bo na ludzie przychodzą.
No właśnie.
Więc
Dobra.
So since we still have a little bit of time, we will wait. You can maybe grab a quick coffee and come back because according to the plan, we're supposed to start at 2:40, and since people are switching groups sometimes to join the talks, we're going to wait just a little bit more than 10 minutes to allow everyone interested to join.
what's funny, right, good. I didn't either, but basically the first night I was sat next to this guy, and then clear we were on. I got the gist and we were talking about it, he'd said, and I looked afterwards. So yeah, I was just always like a little guy, and I was like, oh shit, you actually are right. You're basically like a celebrity. Yeah. I think there was one guy that I could not actually very clearly. But it is interesting that yeah, I guess he is now. No, it's so annoying. I refuse to let them. Yes. Oh yeah, you see, you get. Yeah. Cool. Like. I'm just searching. Because it's called he also. So my point is just to show it. So yeah, it's just me. Right.
Yeah, that is fundamentally.
Very hard to there was because I did another talk with and my talk wasn't did actually search it. I was after we produced my slides. I was just curious if anyone else had ever like I just basically searched my website Euro and it came up with this
It's just like this data useful. They are using that's more than they are
You mean like
yeah, people follow around the kind of stack of everything on the notebook in a way that
I know which ones I went to. I know I have a record.
and that is just like the convenience of having the notebooks is getting people to the stuff that
I was decent.
making it out of their own mind.
yeah.
Anyway, do it.
Did you
Yeah, I want to
find
yeah, I remember there's four places. Yeah, two more.
Oh yeah, that's what it's about. It's like values being I think that's like already a solution of cyber violence. I think actually it's already solving a lot of the issues like
I guess this is always
the kernel is there, but it's not like you're keeping the kernel alive, like if you turn off your computer, it dies forever. It's more like, okay, it can run this script at this point, and then I can still run this script as if it were running on the file, and I can load the document and get loaded from the node. So, I know, it's like switching to anyone. Still using notebooks, but you are trying to patch more the you don't want to do that.
I think it's like some they have started learning programming
Yeah.
and it's or something. So you basically play with comments well, that's the thing. Code inside.
You still have the problem that if you are inside like that you are speaking your kernel, so you can run cells on the bottom.
Oh, okay.
It's just that thing you still need to keep in mind, but instead of having all the problems of like mostly
So you have VS Code installed. Because you say you don't need a lot of
that's
I mean, you need it's just that maybe you can have
Is it an option problem? I mean, for me, I usually just follow it's for me a bit more.
Yeah.
There is another noise going to say, which is just a better kind of developer than you know. I don't know if there are like you can also just write it as if it were plain and use stuff like GP text that I'm read this and convert this into a notebook. So you don't necessarily need VS Code, it's just like my step if I use code for everything. So
training and drinking everything is like a reliable recipe to get like really solid the next day.
but VS Code is VS Code.
Yeah.
Is it like
Yeah.
I haven't used it. I know that there is VS Code.
Okay, so welcome back, everyone, and please get ready for our next speaker, Agnieszka, who will ask us a very interesting question: can your research notebook survive a code update?
Thank you. Hello everyone. I'm happy to be here. I'm Agnieszka Żaba, and together with Sylvester Arabas and Open Atmos contributors, we presented this, prepared this presentation. It is also available as a Jupyter book, and I will show at the end of the presentation QR code for this. I'm from environmental physics group here on IGH, University of Krakow. And I'm a part of Open Atmos community here in Krakow. We have a small group. You have a chance to look at two posters from our group by Michał Groński and Aleksandra Strąbała, and I'll present some of our work and try to answer how we approach maintaining reproducibility with continuous integration and automated testing. Throughout the presentation, at the bottom in the footline, there is a GitHub page for our Open Atmos repositories. Okay, so I want to answer why we're talking about reproducibility, why we consider notebooks, and I will present some of the projects from our group that will serve as examples of developers and users' perspective on maintainability. So let's start with what we mean by reproducibility. I'm talking about reproducibility of research results, and here from geoscientific model development, here's a journal that provide guidelines how to achieve reproducibility, because if we prepare a paper and we have some code, it's not enough to explain the method in the paper. We need also the code in files and other files that here all of the input data to actually reproduce these results. So we need this input data, we need configuration files, no manual processing of the data. Sometimes it is not uncommon that even an author of the paper cannot reproduce their plots after a couple of years. And the guidelines states that all figures and tables must be scientifically reproducible from the scripts. So we want to address these requirements from journals, and also want to address why actually notebooks, why we have notebooks in our code base. I will not answer by myself. I will cite here a paper from Nature, why Jupyter is data scientist computational notebook of choice. It's by Perkel from 2018. And he stated, we went from Jupyter notebooks not existing some 6 years ago to, in essence, everybody using them today. And then he say about this that it's difficult to organize this code in a notebook. It's difficult to break it in reusable models and develop tests for this. So their notebooks are used in scientific research, but also they have a lot of difficulties and challenges that we want to address. The same author, three years later, published another paper, and he cited a study from 2019 that found that just 24% of almost 864,000 publicly available Jupyter notebooks on GitHub could be successfully re-executed, and only 4% produce the same results. So we all know that this is a very big challenge, and in the next slides of my presentation I want to show you how we address this in our Open Atmos community. Packages that I want to present as examples are started over 5 years ago, so might be good as for discussion about maintainability. First of the packages is a PySDM for simulating diffusional growth and breakage of particles in atmosphere and dynamics of these particles. It's an implementation of Monte Carlo super droplet method introduced in Shima et al. 2009. The other one is PyMP data. This is a Pythonic implementation of Smolarkiewicz MP-data algorithm, and it is used for solving advection diffusion partial differential equations. More about this is on poster. And here is very small package that is just for some utility routines for Jupyter notebooks and help us maintain them within this PySDM and PyMP data code bases. And I want to show some of the functions that are inside this small open Atmos Jupyter Utils package. Okay, so from developers' perspective, we will start. Here are some what developers can gain in and what actually is important for us. So we need some inversion of control and modularity, and if we have this, dimensional analysis can be obtained. Also, we need to find some testing scenarios. We need to onboard new developers. So how we do this in our packages? It is based on PySDM, this example. Modularity and inversion of control is a prerequisite for reusability in atmospheric science for testing. And in atmospheric science, it's not uncommon that people are using different parameterizations, different simulation flow control for their experiments, different environments. So it forced us to actually have a modular structure. And I want to show this based on an example that is reproducing findings from Boll in 1958. He was researching on amount of tritium in the air during Cold War and how much of this tritium will be in precipitation and reach the ground. And here we can see this is a snippet of our code. This is what we want to look here and see that all this is from Jupyter Notebook based in PySDM, and the user can choose which formulae they are using, if they are several in literature, different parameterization for example, saturation vapor pressure, so we can define which one we want to use. User can also define their own constants and the values of them. And because of this modularity, it's easy to perform dimensional analysis, writing like here the code for example, here a unit of tritium formula that is presented in my Bollin's Jupyter notebook. This is important that this test is outside of notebook, so we can perform it on CI on GitHub. And developers may stumble upon a difficult problem, what to test and what scenario we want to test. So if we want to reproduce our examples, are reproducing results from research papers, so it's easy for us to set a scenario. We just want to compare our result with those from papers. So we don't need to think about edge cases because we have them already. So we can just install this package OpenAtmos Jupyter Utils and using notebook vars function and PyTest fixture, Like here, we can execute unmodified notebook code for automated testing. It's run once. Multiple asserts is outside of the notebook, and during development of our code base, if anything changes, there is a smoke test that will show us that previous results are not correct with the new utility, for example. So I want to show. I will show some. What is this Jupyter notebook in my PyCharm, and what is important here? We have formulae chosen by user. We can perform dimensional analysis. Unit tests are outside of the notebooks, and it's easy to onboard new developers, because if you have modularity, we don't need to know all the whole code, whole repository. We just need to understand some part of this. So here in examples we have a lot of. Oh no. Okay, a lot of examples. For example, here is this volume table, and for testing we can test against the values. And I just want to from here show that here we have not test by PySDM. In PySDM, for example, there's a submodule physics, and thanks to this, that there is a structure submodule you can test all the formulae and parameterizations. Okay. Now user's perspective. So for users, it's important that it's self-contained and ready to run. You can render a vector graphic that I will show in a moment, and maintainable visuals that are maintained during development of the code. So from OpenAtmos Jupyter Utils, you can use showplot. You can save it, like here you have buttons to save it as PDF or SVG graphic and put it in your paper. Same for animations. You can render this. And what's important here, that they are generated inside the Jupyter notebook, so we don't store files in our code base. We just regenerate them, so we don't need to check all the files if they are correct. Okay, I will show just not here. Okay, and here, for example, is documentation for PyMP data, and user can go into examples, choose an example that he is interested in, and we have badges that you can render this on GitHub, launch on Vider, or open in Colab, and the graphic, the animation from this is generated by this code. Okay, and now I want to go to the summary of my presentation. So if we have research notebooks in our repository, it's important to have automated testing, because then we have obtained reproducibility. Modularity and inversion of control improves usability and accelerates onboarding and enables dimensional analysis. If we have generated and embedded visuals within our Jupyter notebooks, then it increases the likelihood that outputs remain consistent with the code and are easier to maintain. And throughout ongoing development, we need this automated checks. And I want to just show at the end this where you can find more information about this presentation and our packages. Here are some acknowledgements, and here is the. I will just go back in a second and not this. Here it looks like this. It's a Jupyter book that you have all the information that I showed here in this presentation, and links to our OpenAtmos packages. Okay, and I'll go back and thank you for attention.
Thank you so much, Agnieszka. Do you have some questions?
Yeah, thanks for the talk. Yeah, I'm very interested in this idea of like testing notebooks. So often in my work, I'm like working in like less sort of thought out projects than the one you showed. So if you're just so basically just working on like a single notebook or so in an analysis, but if one wanted to implement testing in those notebooks, in your experience, how is like writing tests for notebooks in general different from just writing regular tests for regular Python script? Is there like a general difference in how you would test notebooks, maybe with respect also to plots and so on? So how can you verify that the plots stay the same and there's like no like subtle differences?
Okay, thank you. So what we have here, there's not much difference. The difference is that via this notebook vars from OpenAtlas Jupyter Utils, we executing the code and store the variables from the notebook, and then we test the values. So we do not test the plot as it is visualized, but we can test the values that are there. So probably we're not testing here if they are the same, but if they are within some margin that we want to achieve. So you can use it and also for one notebook with this PyTest fixture. You can write your own test, and it's the same. It's just you need to collect the variables from the notebook.
And you're testing them cell by cell, the notebooks?
We're executing this and checking the outputs. We have a test for the outputs, and we're running this on CI on GitHub Actions.
Thank you.
Thanks for the talk. My question is more general, I would say. So now we can write Python files and just execute them as if they were notebooks, pretty much, using VS Code, for example. You can, which avoid some of the issues with a notebook. My question is, so the premise, I don't like notebooks.
Okay, I don't say that they are great. I say that they are there and everyone is using them, so
Okay.
we want to adapt. But
so, like, I guess that my question is, the intent for this project is to put a patch on the notebooks that are already there, because, or rather, notebooks have some shortcomings that the project is trying to address. But you're not claiming that. I don't know. Let's not ask it this way. Do you believe that? So I don't want to be polemic in this. It's just that to me, from a point of view, seems like this is trying to put a patch on a tool that is not being used properly. Or it is being used in a way that it's kind of avoiding them of trying. You're trying to get around the problems of the notebooks.
okay, so the notebooks are only the the examples. There is PySDM and PySDM examples, for example, and there we try to reproduce this scientific research, but then all of the simulation or of the code is in Python, not in notebooks. But yes, probably if someone wants to use it in a different tool, not in Jupyter notebooks, it's also good. We decide on this and we use this because it's easy for users. They can open this on Colab, for example, and probably if there will be a tool that will suppress these Jupyter notebooks, then we probably adapt to this. But right now there are two use cases. One of them is people are using examples and can take how they can achieve their experiments, and the other one is they are using just for MIDI and Python code. So yeah. But yeah, I don't say that Jupyter notebooks are the best for everything. They are just there, and
It makes sense to like.
And we want to test them because, as you can see, there are many ways that you can achieve different results. You rerun this and you have everything different. Someone else is running this, it's different how to check it. So it's needed to test it automated.
Yeah, it makes sense. Thank you.
Thank you.
I was going to make a counterpoint to that. I also hate notebooks. However, like some of the quite a lot of scientific code I've worked on have had like an examples bit called downstream users bit, and that use case is quite nice. They're in like the Sphinx documentation with some steps and plots or whatever, and like we do things like clearing the metadata so at least they don't change every time you change and check the execute, but it's not actual testing. So I do like the idea of having an actual way of testing it. So I might try this.
Yeah, and we are not clearing metadata because we're using this for checking. You can use on GitHub, there are rich diffs, and you can see plots from previous code and your new commit, and you can compare, but we are not clearing them.
Yeah, but I guess when I say clear metadata, what I mean is things like the run numbers. So
cell
one,
at the
cell
time,
two. If you run that, and now it's 5, that would be a change, when really it's not a change.
Yeah, but we actually want to keep it like we're checking if they were executed and if they were executed in order. Because then author can get results, but if you run it in order, you have a different result, for example. So we're also checking this.
I'll show you what I mean.
Okay, yeah, thank you.
I think we're running out of time, so maybe one last question.
Thank you, really enjoyed the talk. I'm just wondering, there's been a lot of hype around Remo as an alternative to Jupyter Notebooks.
Could you repeat?
There's been a lot of hype around Marimo. It's a new kind of Jupyter Notebook alternative, and one of the benefits is not only it allows you to define everything in vanilla Python files, but it also allows you to include test utilities natively within alongside the notebook, as well as run PyTest on it. I'm just wondering if that's something that your team has explored.
Not that I know of about this. I heard it first time, and we aim to have tests outside of the notebooks. So everyone can create a notebook, but I'm not familiar with this name.
Okay, no, that's all good. I mean, it's one of those things where it's like, I'm also not familiar.
Okay.
A lot of people are familiar, and it's also very different to whatever's been built.
Could you spell this?
Marimo.
Okay.
Yeah, it means a ball of moss. Like it's a type of moss. Anyway.
Okay, thank you.
Yeah.
Let's thank Agnieszka again. And let's go get some coffee.
So all I need is just to say, so what I mean is that these are like they don't have the and they also don't have things like but they still have the way you choose, and this just makes things
Okay, so it's last similar to notebooks and
no, this is just